All right. Hi, everyone. Welcome to the forum on robotics and control engineering. My name is Tansel Yusulun, and I am an assistant professor at the Department of Mechanical Engineering of the University of South Florida. At my university, I am also the director of the Laboratory for Autonomic Control Information and Systems. With the support from my university, I am very proud today to host Dr. Maria Prandini from the Politecnico di Milano to participate in our live seminar series on control systems through the FORCE. I would like to say a couple of words about the FORCE, and then I will introduce Dr. Prandini. So FORCE is dedicated to provide free, high-quality outreach events and online seminars to reach broader robotics and control engineering communities around the globe. To support our mission, we periodically invite distinguished lecturers like Dr. Prandini to give talks on recent research results related to robotics and control engineering. As such, the FORCE aims in connecting academicians and government industry researchers, practitioners with each other through cross-cutting research and education discussions. We cordially hope that you will enjoy all the FORCE events and find them valuable to your own research interests. Let me mention a couple more things about robotics. During the presentation, you are all muted. Please ask questions after the presentations, and you can do so by virtually raising your hands through WebEx, or simply you can unmute yourselves. Or you can, session is being recorded to be posted to the FORCE website through YouTube. So if you do not wish to have voice included, you can also use chat, directly send questions to me, host, and then I can read them to Dr. Prandini. All right, so I am very proud again today to host Dr. Maria Prandini. She received her laureate degree in electrical engineering from Politecnico di Milano in 1994 and her PhD degree in information technology from Università di Brescia. She was a postdoctoral researcher at the University of California at Berkeley between 1998 and 2000. She also held visiting positions at Delft, Cambridge, Berkeley, Swiss Federal Institute of Technology in Zurich. And in 2002, she became an assistant professor in systems and control at Politecnico di Milano, where she is currently a full professor. She's a member of IFAC technical community on discrete event and hybrid systems since 2008, and of the IFAC policy committee for the Tranium 2017 and 20. She was editor for CSS Electronic Publications, elected member of the IEEE CSS Board of Governors, and the IEEE CSS Vice President for Conference Activities. She is a senior member of the IEEE. Her research interests include stochastic dynamical systems, randomized algorithms, distributed and data-based optimization, multi-agent systems, and the application of control theory to transportation and energy systems. For all of you who are here live for the presentation of Dr. Prandini, first I would like to thank you very much, Maria, for participating in our forum. And we are ready whenever you are ready.
Okay. Shall I start?
Yes.
Okay. First of all, I would like to thank Tansel for the kind invitation to join this forum on robotics and control engineering and share with you a recent result of my group on multi-agent distributed optimization of our networks. So I'll start motivating the problem we address. There are multi-agent systems over networks are pervasive in many domains, including social networks, robotic networks, automated transportation systems, and energy systems. And actually, we started working on energy systems, which motivated our contribution to distributed optimization. And our goal was to optimize the performance of a network, developing a unifying framework where we could account for different characteristics of a network, like the fact that it's a large-scale system with multiple interactive components. It is multi-agent in the sense that each component has computation and communication capability. Each agent might have different physical or technological constraints and different objectives, so it's an heterogeneous system. typically affected by uncertainty. So uncertainty can affect the system, the network, because of some parametric or model uncertainty, or some disturbance, so exogenous uncertainty. And uncertainty can affect the system globally or locally to each agent. Another characteristic that we try to account for is the combinatorial nature of the problem, which arises when you have to take decisions that are not only discontinuous but are also discrete, and this is generally a challenge. We try to develop a comprehensive framework addressing the following challenges: computational challenges, which arise because the problem size when you have a large-scale system may be too big, and when we have discrete variable, it can be even combinatorial. Communication challenges are related to the fact that if you adopt, for example, wireless communication that are local, not all communication links may be valuable, and there might be link failure. And also, agents are willing to cooperate for optimize the performance of the overall system, but they might be not willing to share their own local information with everybody. So we have to provide guarantees on privacy of local information. And then another challenge in the solution of optimization problem over a multi-agent network is that uncertainty must be accounted for. If you neglect uncertainty, you most probably end up with a solution that is then unfeasible. And often uncertainty is not fully available with a full description, but is often known only through data. So for addressing these challenges, we actually developed a distributed database optimization framework where we look for an optimal solution by solving in parallel smaller optimization problems local to each agent. And each agent has available information on uncertainty through local data. And we want to account for uncertainty when determining this optimal solution. So we decided to go for a distributed solution methodology because it's scalable. Scalable with respect to communication, because you can limit communication only between neighbors and exchange a limited amount of information. Scalable with respect to computation, because when agents solve the local problem, it's smaller than the global one. And also is resilient to communication failure, because you don't need all information to be conveyed to a central unit, which might be critical if some link fails. And also you can guarantee information privacy, so the agent do not need to reveal information about their objective and constraint function to each other. So the rest of the presentation is structured in 3 parts. We first address the deterministic case, describing the setup, our proposed algorithm, the results on convergence, and the relation with other methods in the literature. Then we rephrase the problem in stochastic setup, proposing a distributed database solution. Then we move to a different class of problem that we call the constraint-coupled problems. And here we'll see an alternative distributed dual decomposition algorithm, and we also address a discrete case. And finally, I will summarize what I described, and I will briefly sketch our future work. So as I was mentioning you, we started from an energy management application, which was inspiring for motivating our work on distributed optimization of our networks. And this will be an example that I will show also further on during my presentation. So we are considering a set of buildings in a district. So each building is equipped with its own chiller plant and is sharing with the others a cooling network that can be viewed as a thermal storage device. And the goal here is to determine the joint use of the storage system, which is a shared resource, plus the temperature set point in the thermally controlled zones within each building. so as to minimize the cost of electrical energy consumption of all the chillers in the district. So I will just outline a high-level description of the problem without writing equations at this stage, just to motivate the framework. So what's a chiller plant? Is a device which converts electrical energy into cooling energy. And it can be characterized via a coefficient of performance, which represents the ratio between the cooling energy and the electrical energy. So you can see in this plot three different characteristics of coefficient of performance as a function of the energy production, cooling energy produced by the chiller, which relates to a small chiller, the red curve, a medium-sized chiller, the blue curve, and a yellow curve, which corresponds to a large-sized chiller. So the idea is that the chiller operates at higher efficiency if it's closer to the maximum of the coefficient of performance. So different chillers have different characteristics and different best operating points. When you address the problem of minimizing the overall energy consumption in the district of buildings, you are basically resorting to a model where you have to write an energy balance equation. And to this thermal energy balance equation, there is a contribution of the building which consumes energy. It requires cooling energy to maintain a certain temperature, which is a comfort temperature for the people that occupy the building. And when you account for a model of the building, you have to account for different contributions. So you have to model the wall zone energy exchange, which represents the building thermal dynamics. You have to account for the thermal energy produced by people that occupy the building. You have to account for zone thermal inertia, and then other internal energy contribution, which relates, for example, to the short wave and long wave radiation, solar radiation that enters through windows or the internal lighting. And you can think about writing equation. Actually, we wrote a paper on this specific application, but I'm not interested at this stage of writing the details. Then you have as a key ingredient that creates the coupling, the thermal storage. And for the thermal storage, it's a simple model, so I wrote it down. You have that the cooling energy accumulated in the storage is the integral of the cooling energy that are provided by the different chillers, with a sign that is positive if the energy is drawn from the storage, and it's negative if it's charged to the storage. So you have a summation of contribution with this minus due to this sign convention. It's actually not really an integrator model because you have this alpha coefficient, and the alpha coefficient is typically smaller than 1 to account for energy losses. So if you write the optimization problem, you're actually minimizing, as I told you before, the sum of the cost of the electrical energy consumption of the different chillers that are owned by the single buildings, and you have constraints related to an energy balance. So the thermal energy request, the cooling energy request to the chiller is given by the building's energy request minus the storage energy. Then you have as a constraint the storage dynamic, which I described you before. And then you have the storage limits in the sense that the storage can have a certain capacity, the chiller production limits, and then comfort constraints related to temperatures. And the optimization variables are, as I told you before, the exchange with the storage and the zone temperature set point in each building. So if you collect the decision variable, temperature set point and storage usage in a vector X, for example, the temperature set point and storage user typically during 1 day time horizon, you end up having a problem of the following form. You are minimizing the sum of objective functions, each one related to each single building, so each single agent, which is the cost of electric energy consumption of each chiller, subject to a constraint that is actually the intersection of the constraints over all buildings. And the decision variable is common to everybody. This actually creates a coupling. So the objective functions are local. Fi is the objective function for agent I. The constraints are local. Xi is the constraints for agent I. But the decision variable is common. And this creates a coupling between the problems. So you can think about solving the problem globally, centrally, or distributing it. And actually here I'm describing a proposed distributed algorithm for addressing this decision coupled problem. So the idea is that each agent, so let's say agent I, is minimizing its own local cost, Fi, with respect to its local copy, Xi, of the decision variable. It's minimizing this cost subject to some penalization, which is this function g of xi zeta, where zeta is an information vector that is constructed based on the information collected from the neighbors of agent I. And then agent I is solving this minimization problem subject to its local constraints. So it's using its local information on Fi and Xi, plus additional information that it gets from the neighbors. And out of this minimization problem is deriving a solution, Xi star, which will be a function of this information vector Zeta. So this is step 1 of an iterative procedure. Step 2, agent I broadcasts its solution, tentative solution to the optimization problem to its neighbors. Here the neighbors of agent I, depicted in green, are those ones to which building I is directly connected, here in this pictorial view. At step 2b, you receive information from the neighbor solution, and then agent I update information, the information vector zeta I based on the information that it receives, and go back to step 1. So I need to specify for the problem to be well defined the information vector zeta I, and also this penalization proxy term g xi zeta I. So the information vector is a weighted average of the tentative solution of the other agents, the neighbors, while the proxy term, it's a term that penalizes the deviation from the weighted average of the neighbors. And it's trying to enforce consensus, so convergence of xi to a common value among all agents. Ck is an important term because it's the weighting coefficient that determines the trade-off between the thermality according to Fi, the local objective, and the agent disagreement. So it will be key how this Ck behaves along iteration. This will be key for convergence, and convergence eventually to the optimal global solution. So the natural question at this point is, does this algorithm converge, under which assumption, and if it converges, does it converge to the same solution of a centralized problem? So there are some assumptions for proving convergence to the optimal solution, and these are the standard convexity and compactness assumptions, which are typical of optimization in general, and in particular distributed optimization. So Fi convex, Xi compact convex, and non-empty interior. And as for the choice of a proxy term, it's non-increasing. It's important, it's rate. So the summation of Ck should be infinity, but if you sum the square, this should be bounded. So for example, an harmonic series like 1 over k plus 1 satisfies this assumption. This is key because you have to penalize the disagreement with respect to the other agents, but appropriately not to lose optimality. It's important also how you account for the information of the other agents, in particular the neighbors. So these weights A, I, J, K are time varying to account for the fact that, for example, a link might be not available for some time. They are 0 if there is no link between agent I and agent J. And if they are non-zero, so there is a link, they have to be lower bounded by some constant, so as to guarantee that the information mix and spread out at a non-diminishing rate. So if you interpret I as the index of rows and J as the index of column in a matrix, the matrix A with element A, I, J, K should form a doubly stochastic matrix whose rows and columns sum up to 1, and this is to guarantee that agents influence each other equally in the long run. Not surprisingly, we need further assumption related to network connectivity. So if there is no communication between agents, it's impossible that you get convergence to the overall performance the common welfare solution. So what you need is that eventually all information flows, so any pair of agents communicate infinitely often, and you have a bounded intercommunication time. So this means that if you build the graph that has as vertices the agents and as edges the links that are active infinitely often between two agents, this graph must be strongly connected. And the intercommunication time between agents that are directly linked must be bounded. So for example, in the ring that I drew in this slide, green represents active links, red one inactive links, and if I alternate like this, you have a network connectivity assumption satisfied, because the graph that I was mentioning before is strongly connected, and the intercommunication time is 2. Okay. So under the structural network assumption that I made previously, we were able to prove that the proposed proximal algorithm converged to a minimizer of a centralized problem, so that you can get asymptotically in the iteration, agreement, and optimality. So a consensus solution to the optimum for the centralized problem. The rate of convergence is related to CK, so it cannot be faster than CK, which in turn should be slow enough to trade agreement and optimality. So there are other algorithms proposed in the literature for solving the same kind of problem, and in particular gradient and subgradient methods. I'm referring in particular to this paper by Angelija Nedić as first author on constraint consensus and optimization in multi-agent networks, where it's exactly the same kind of framework except for the constraint set xi, which must be identical for all agents. And then compared to our proximal algorithm, the key step per iteration is the projection, the second equation, so the projection over the constraint set of one step of gradient, evaluated in the information vector, so that weighted average of a tentative solution of a neighbor agents. Under the same assumption as ours, and under the same rate of convergence to 0 of CK, you get actually convergent to one minimizer for the global problem, so a consensus optimal solution. So the difference between our proximal algorithm with respect to gradient subgradient algorithm is that you don't need gradient subgradient calculation, but in turn you actually need to solve an optimization problem. which in the case in which the objective function fi is, for example, quadratic and the constraints are linear, it's simple. It can be tougher to solve in case of a generic convex function. We can tackle the problem with a heterogeneous constraint set with respect to this work on gradient algorithm, and we don't need differentiability assumption. These differentiability assumptions are not needed in the case of a subgradient algorithm, but what you can have, it depends how you're able to, how you compute the subgradient, is actually an oscillatory behavior. So this plot is taken from a paper where we actually compared proximal with respect to subgradient distributed optimization algorithm. And we noticed that when the cost function was not differentiable, the subgradient produced some oscillations. This is not the case if the cost function is differentiable, and they are really with the same performance. Okay. So I'm now showing some simulation results where we apply the described proximal distributed optimization algorithm to the building district problem. So for ease of explanation of the result, I'm just considering 3 buildings, and each building is divided in 3 thermally controlled zones, each one corresponding to a floor. So zone 1 is the ground floor, zone 2 is the intermediate floor, and zone 3 is the second floor. Each of the 3 buildings has a different chiller, so a small, a medium, and a large size chiller. And we consider the case in which we have pairwise communication, so the gossip scheme of communication. Yeah, you can see it in this short animation. So we implemented our algorithm in MATLAB using as solver sedum-me through the MATLAB interface YALMI. And what we got is, for example, the consensus solution in terms of zone temperature profile for building 1 is the plot here in the slides, where you can notice that the zone temperature set point for zone 2, so the intermediate one, the green one, is lower than the others, which means that the solution exploits the intermediate floor as a passive thermal storage, since it can drain heat of the other zone through the floor and ceiling. As for the usage of the storage along this 24-hour time horizon, if you look at the solution computed by the building which own the middle size chiller at iteration 1, where the building has not yet any information on the tentative solution of any of the other buildings, so on the need of the other buildings, you can see that the blue line, which corresponds to the usage of the middle chiller building of the storage, is all with positive value. You should look at the labels on the right side, which correspond to the energy exchange. So positive means drawing energy from the storage, I recall you. So the blue one, it's always drawing energy, while the other 2 buildings corresponding to the yellow and the orange lines are charging the storage, because they correspond to negative value of the energy exchange. If you look at the consensus solution, so the optimal solution, when the algorithm has converged, the situation changed completely. And you can notice that the blue line is the intermediate one, so the middle the middle chiller building is partly charging, partly drawing energy from the storage. The yellow line corresponds to the large size chiller, and this one is all the time charging the storage, because it corresponds to negative value if you look at the labels on the right hand side of the plot, while the small chiller building, the orange line, is always using the storage charged by the others. So at the end, the buildings are basically sharing their chillers, their actuation systems, thanks to the sharing of the storage. And this is quite interesting. So if you look, for example, at the coefficient of performance behavior of the three chillers along the 24 hours time horizon, when you assign to each one of them a fixed fraction, 1/3 of the storage, only the medium-sized chiller is operating at high efficiency. It's the blue line on top. But if you let them share the storage according to the consensus solution that I just showed you before, all the three chillers are able to operate at a high efficiency. So you get an advantage in sharing. Sharing is good for the community. So we actually computed a solution referring to a nominal setup, where the disturbances, which are represented by occupancy, people occupancy, this yellow line, outside temperature, the red line, the dotted blue line is a low wave radiation, solar radiation, short wave radiation is the purple one, were at nominal value. But actually, if you look at the behavior of a solar radiation, it's actually really changing day by day. And so the risk is that the solution you compute without accounting for uncertainty, it's unfeasible when you try to apply it in practice. So in some applications, it's actually mandatory to account for uncertainty. So we have to move from this deterministic setup to a setup with uncertainty. And here the formalization is simple. We just add a parameter delta, uncertainty parameter delta, to the constraints, the local constraints. This might appear a restrictive assumption, but in fact it is without loss of generality. You can do it because in case also the objective function were subject to uncertainty, you can adopt an epigraphic reformulation, so basically upper bounding the cost through an additional auxiliary variable, then use this additional variable as cost and introduce the bound among the constraints and reduce your formulation to the present setup, which is shown in these slides. So without loss of generality, we refer to decision-coupled problem with uncertainty, where uncertainty is actually affecting just the local constraints. So it's exactly the same formulation as before, except for this uncertainty parameter. So delta might represent an exogenous and endogenous disturbance. So you might think about a disturbance realization in the case of the buildings related to occupancy profile along the day, temperature, external temperature, solar radiation. And this capital delta is the set where uncertainty takes value. And so we adopt a stochastic setup, assuming that the uncertainty realization are governed by an underlying probability distribution over this capital delta set, which is generally a continuous set. So if it's indeed a continuous set, the problem formulated above is a semi-infinite optimization program in that you have a finite number of optimization variables collected in X, D variable. In the following we shall denote the dimensionality as D. And then we have an infinite number of constraints if capital delta is a continuous set. So semi-infinite optimization program, except for if some specific structural cases, are generally hard to solve. Also, a problem is that uncertainty is typically not known explicitly, not even the set to which it belongs, but is typically known through data. So the idea is to replace capital delta with the set S of samples of uncertainty. This brings us to this decision-coupled problem with uncertainty with a finite number of constraints, because delta now belongs to a set, capital S, of samples. So we are going next to address two cases. The case in which each agent has the same data set, capital S, and the case in which uncertainty is known locally to each agent through different data sets, which are denoted here in blue as SI. So we start with a simpler setup of a common data set, and the first question is, can we obtain a distributed implementation of this decision-coupled problem? And the answer is yes. We just need to use the intersection of local constraint xi delta over the samples capital S in place of xi, and then you can apply a distributed optimization algorithm like the Proxima algorithm that I showed you before. So what you're going to get is a solution X star S, which is optimal for this sampled program. Now the question is, but the problem that I wanted to solve was different from this sampled program, database program PS. It was a robust program P capital delta. So is this solution that we compute according to the distributed algorithm feasible for this robust program? And does this hold true for any sampled set, for any multi-sample capital S? So we can actually provide probabilistic guarantees on the quality of this solution and on its feasibility by using results that were developed in an IEEE Transactional Automatic Control paper of 2006 by Giuseppe Calafiore and Marco Campi, according to the so-called scenario theory for stochastic optimization. So the result reads as follows. If you fix a confidence parameter beta and you are given a certain sample set capital S, then you can state that with confidence larger or equal to 1 minus beta, the solution X star of S is feasible with a probability that is larger than 1 minus epsilon. So the violation set epsilon, the violation set where the constraint is not satisfied, so the set of delta such that X star S doesn't satisfy the joint constraint, as a probability measure P, which is upper bounded by this epsilon. And this epsilon is actually a function of D, which is the size of the decision variable, the number of samples in the set capital S, and this beta parameter. There is a formula, it's actually a conservative approximation of epsilon, explicit in all this quantity. And what you can see is that the violation is logarithmic in beta, so that beta can be set small, let's say 10 to the minus 5, without increasing too much the violation. It's proportional to D, the number of optimization variable, and it's inversely proportional to the number of samples that are available, so that as it is intuitive, the more data you have, the better the result. So this was for the common data set, and then we move to the interesting case of different data sets. I would like you to notice that the data on uncertainty might be part of a private data. In the energy framework, for example, the consumption profile of each building is a private information and is uncertain. And buildings are not willing to share this information with the other, although they might be interested in getting a lower cost for the overall district. So it's important that also this kind of information is kept private, and also sharing it, making it common, means communicating it, which requires some time and a burden over the communication link. So this is an interesting case, in my opinion. So as for the distributed implementation of the overall optimization problem, it's still easy, like in the case of common data set, in the sense that it's just a matter of interpreting the intersection over the local over the uncertainty of the local data set of xi delta in place of xi, and then you can apply proximal or gradient algorithm, distributed algorithm, to find the solution to this problem. We denote it still with x star of s, this converged solution. And what it's easy to show by applying a result that was proven recently in a paper presented at the Conference on Decision and Control in 2015, authored by Marco Campi, Simone Garatti, and Federico Ramponi, is that for each single agent, there is this kind of result which resembles the previous one. So the probability that the local constraint xi delta is violated for if you see a new uncertainty instant delta is upper bounded by this violation epsilon I with confidence larger or equal than 1 minus beta I, local to agent I. And this epsilon I is a function according to the same formula as in the previous case, but of beta I, cardinality of Si, and this di Si, that it's the number of support samples that you can observe a posteriori of agent I. What I mean by support sample here is a pictorial view. So let's say that you have two agents, and your optimization variable are two, let's say xi in the horizontal axis and x2 in the vertical axis, and you are minimizing x2. So in this plot, the green lines represent the constraints of agent 1, and the blue lines, the constraints generated by agent 2, the local constraint associated with its SI, S2 set of sample data. So in the plot on the left, the support constraints at one effect, if you remove them, you get a different solution, and they are the one such that if you preserve them, the solution is identical to the case in which you put all constraints. So the support constraints are one, a green one for agent 1, and one for agent 2, a blue one. Instead, on the plot on the right, you have that the support constraints are determined just by agent 2. So D1 S1 is 2, and D2 S2 is 2. So the result I show you in this slide, it's a posteriori result in that it depends on the number of support constraints per agent, which depend on capital S. So from the result for a single agent, by exploiting the subadditivity property of the probability, you can easily find a bound on the violation with respect to all constraints. It's just upper bounded by the sum of this epsilon I. This is still an a posteriori result, and then we ask ourselves, can we turn this into an a priori statement so that we can assess it without looking at the actual solution? What's the expected violation? What is the worst case value of this summation that we can observe? And this actually can be computed, estimated by this simple observation. Since this is a convex problem, we know that the number of support constraints is upper bounded by a number of optimization variable D, and this holds true for every agent. This is a conservative bound because actually you know that the summation of all DI is upper bounded by D. So we can use this sharper bound, and if you decide to use this sharper bound, you actually have to solve an optimization problem and determine epsilon as the maximum of the summation of this epsilon I, subject to the constraint that the sum of the DI is upper bounded by D. This is quite convenient, and indeed you get a quite sharper bound. So the green one is the one that you get with a common data set, and it's how the probability of violation grows with the number of agents. The blue one is the one that you get by using the less conservative bound in the case of private data set. If you would use the conservative bound, instead you'd get the orange plot, which is growing fast. So it's convenient to use the blue one. Alternative approaches in the literature. There is actually the closest approach for the problem setup, kind of problem setup, is the one in this paper by Lee and Edich, Distributed Random Projection Algorithm for Convex Optimization. They get a stronger result of almost sure convergence, but they need to sample constraints infinitely many times, which means that it's not really a data-based approach because you need infinite data. So at the end here, you need the model for the stochastic uncertainty to extract it infinite times. While in our solution, we get a weaker guarantees because we are just in probability, this violation probability, but with a finite number of samples. So the problem I described you up to now, it's a decision-coupled problem where the coupling comes from the fact that X is a common decision variable. We also address problem in which the coupling originates from a coupling constraints. So in this setup on the right, you have xi is the decision variable of agent I. So each agent has its own decision variable with a different dimension from the other, possibly. Its own cost fi, its own local constraint capital Xi, and then the coupling ingredient is this coupling constraint sum over the number of agent I of a local constraint function gi as a function of xi smaller or equal than 0. This can represent a constraints, a budget constraints. So you have a certain budget, the agent, and then you decide how to divide it among agents. So local objective, local decisions, and the coupling constraint. So since the coupling constraints originate in the coupling in the decision, you have a constraint coupled problem. Not anymore decision coupled, but constraint coupled. So what we notice here is that if we resort to duality theory, we end up introducing this dual variable, lambda, and having to maximize instead of minimize the summation because of the structure which is additive of the original cost function and also the coupling constraints of local dual function, which you can see on the bottom of this slide, minimum with respect to xi belonging to capital Xi of fi xi plus the dual variable lambda transpose gi xi. So what you can notice is that in the dual problem, we have a decision-coupled problem. Lambda is a common decision variable. The local constraints are all identical, lambda positive. And then you have to maximize phi, the sum of phi I, so additive cost, and phi I is concave. So minimize minus fi is equivalent, and you have minus fi is actually convex. So it fits our original framework to which proximal minimization can be applied, distributed proximal minimization. So this was the idea, and we actually formulate a distributed optimization algorithm, which basically solve according to the proximal minimization algorithm that I described you before, the dual problem by building an average of a local estimate of a lambda j function, and then building solving an optimization problem to determine local copy of lambda I, the common decision variable, based on a cost function that is penalized through this proxy term. And then you need to reconstruct the primal variable. So what we were able to prove for this distributed algorithm under the same structural network assumption as before, the algorithm combining dual decomposition and proximal minimization converges to a set of minimizer of a centralized problem. We are also able to extend the probabilistic feasibility result for the stochastic case to this setup. And then we applied it to the district optimization problem on a simplified version where actually we don't optimize the zone temperature set point, but just the exchange with the thermal storage device. And we have to determine just the use of the storage. We consider 10 buildings with different chiller size, 3 small, 2 medium, and 5 big. Stochastic cooling energy requests coming from the building. Here is just a plot of a few realizations. And then what we got is a similar result as before, in the sense that the blue line corresponds to the big chillers, which are actually charging the storage, while the red one are the small chillers, which are drawing energy from the storage. And this result was given with guaranteeing a violation that is at most 0.25, with a confidence that is almost 1, because it's 1 minus beta, and beta was set to 10 to the power minus 5. So with reference to this constraint coupled problem, but with all local objective function and also the coupling constraints that are linear, we also address the mixed integer case, in which you have both discrete and continuous variable. If you think just about a discrete setup, xi, you should think about a set of points that are constrained in a polyhedral set. So the fact that you have discrete variable makes the problem combinatorial and challenging to solve. So apparently it fits the structure of a constraint coupled problem, but the problem is that it is not convex because of discrete optimization variable. So that if you apply the distributed algorithm that have been developed for convex problems, like the one I showed you before, you cannot provide any guarantees. So we try to develop a solution that at least was feasible, possibly suboptimal, and quantify the quality of a solution and its performance degradation with respect to the optimal one. So in the literature, there are some approaches which refer to specific problem setup. The more general one and the inspiring work of our development was this paper of 2016 in Automatical, a decomposition method for just-scale mixed integer linear programs with performance guarantees and the power system application. And it's a duality-based approach to recover a feasible solution with suboptimality guarantees. The idea of this method was, the basic trick was to tighten appropriately the coupling constraints through a specific amount, which is here called rho tilde, determine the optimal dual solution, lambda star rho tilde, and then recover a feasible primal solution for the original problem with no tightening using this dual. This worked effectively. And what we did is an improvement of this approach by making it distributed with an adaptive tightening of the coefficient rho based on the same idea of the inspiring paper. So what we obtain is that by construction, this tightening coefficient converge to a rho bar, which is typically strictly smaller than the rho tilde of the inspiring paper of 2016. We were able to prove, differently from the inspiring work, feasibility guarantee in a finite number of iterations, and a performance that is typically better than the one of the inspiring paper because of this rho bar, which is typically strictly smaller than the rho tilde. I'm just showing an example where we apply this approach, distributed approach, to optimal plug-in electric vehicles charging schedule. So the problem here was we have 2050 electric vehicles, a fleet, and we have to decide the overnight charging schedule over an 8 hours time horizon, which is discretized in time slot of 20 minutes. So it's 24 decision variables, 1 per time slot over 8 hours time horizon. And the local constraints were the local vehicle capacity, the local target state of charge of the battery at the end of the time horizon. And the coupling was given by the maximum power that the grid can deliver in each time slot. So the goal is to minimize the overall cost of charging the fleet. And at each time slot, we have a discrete time variable, taking value 1, -1, or 0, charge, discharge of a fixed amount, or do nothing. So if you look at the global problem, you have 24 decision variables per vehicle multiplied by 2050 vehicles of the fleet, and 3 value for decision variable. So 3 to the power of 6,000 possible combination. If you look at the local problem, you have 24 times lot, so 24 decision variable, taking 3 value each. So it's still larger, but it's much smaller than 3 to the power of 6,000. And by applying our distributed approach, we could actually solve the problem. We generated 1,000 instances by randomly extracting local parameters of each vehicle to compare it with the inspiring paper of 2016 in terms of performance. What you get is this histogram of performance improvement, which ranges from 3% to 15%. So we could get an improvement with feasibility achieved in a finite number of iterations, as it is shown in the bottom plot, where violation getting smaller than 0 means violation 0, that the problem is feasible. So it's feasible in about, I didn't put it, but 12 iterations. And here you have a plot of a distributed and also a decentralized solution that we develop in another work. And they are comparable in terms of convergence rate. So summarizing, we develop a general framework for distributed optimization over a network, which accounts for different complexity features like heterogeneity of the agency, privacy over local information, uncertainty, combinatorial complexity. We applied it to various problems in energy system, like energy management of a building district, power allocation in a cellular network, plug-in electric vehicle charging schedule. And we are currently working on analyzing convergence rate on the implementation on a rolling horizon to get MPC solution, on developing the stochastic version of a constraint coupled mixed integer linear program with possible application to optimal control of mixed logical dynamical systems, which are a class of hybrid systems that are described by linear inequality and equality involving both discrete and continuous variable. And we wish to apply it to other frameworks than energy systems. So here are actually the main references that were shortly presented in this talk. And I would like to thank and give credit to my collaborators, so my 2 colleagues, Alessandro Falsone and Simone Garatti. Alessandro was my PhD student, and this PhD thesis was on distributed optimization. Constance Margellos is currently associate professor at the University of Oxford, and he was a postdoc in my group for 1 year. And this work was supported by the European Commission under a Horizon 2020 project on unifying control and verification of cyber physical systems. Okay, I would like to thank you all for your attention.
Thanks so much, Maria.
It was long.
Oh, it was great. So, okay. Now we will start taking questions from the audience. Once again, there are a couple of options to do that. And you can basically ask questions by unmuting yourself, but a preferred way is, since the session is being recorded to be posted to the website, if you send your questions to me, as a host, I would love to read it to Dr. Prandini. And while waiting for questions, Maria, I would like to thank you one more time for your availability.
Thanks.
I know this week was not the easiest week, but thanks so much for your time. And,
no, thanks for the kind invitation. For me, it's an
absolutely.
opportunity to share. Yeah, I'm very enthusiastic for this kind of research. And also, we started quite recently because I decided that, multi-agent systems are important, large-scale systems, and we were able to get nice results.
That's right, especially, distributed implementation, so on and so forth. So it was very exciting.
Yeah, still much work needs to be done.
Sure.
Yeah, in CCT there are a lot of groups working on the same topic. So
Oh, I see. Yeah.
yeah, it's challenging.
So, Maria, it happens from time to time. Our audience is a little bit shy. So, like, can we say they can, if they have any questions, can they ask you directly by email?
Yeah, sure. It will be a pleasure also to share some curiosity or some question. Yeah,
Sure.
or some web work to share. I'm happy.
Sure. And by this, I would like to conclude the session. It's 1 p.m. Again, Maria, thank you so much for your time. Audience, thank you, everyone. And our next speaker will be Anna Swami later this month. So then we will continue with the other 4 seminars. Thanks again, Maria.
Thanks. Bye-bye.
Bye.
Bye.